Okay, good morning everyone. Today we are going to talk about iron and nickel on Pourbaix diagram. Um, we are going to look at the Pourbaix diagram using FactSage again. And here's our problem statement. First, suppose that we have nickel-associated iron solid that we want to separate them using electrochemical processes. Using our system, we can manipulate the temperature, the electrochemical potential, and the acidity of our system. In this case, we want to see how we can see the best condition visually. So the Pourbaix diagram is very useful to look at this condition. But first, let's talk about the electrochemical background of this case. So for a reversible redox reaction, you can see that the elements will create an equilibrium. It's the element's product to the power of its coefficient divided by the reactants to the power of its coefficients also. And this equilibrium can be affected by the temperature, pressure, the amount of reactant or pH, as well as the electric voltage. And to express this, the electric voltage, the Nernst equation is expressed. You can see the more detailed explanation about this electrochemical background using this link that I show you in this page. But I just want to show you that the equilibrium can affect the amount of products that we have in the end of the process. And that equilibrium can be affected by temperature, pressure of system, as well as the amount of reactant or pH, as well as the electric voltage. So we're not gonna look into depth in this case. I'll just show you the better video to explain this background. But we will see the Pourbaix diagram on FactSage. We're not gonna calculate the reaction one by one in our case because of course the FactSage will calculate for us, and we click the EPH module in this case, and we will input the variable as follows. We will select two metal elements, in this case the iron and nickel. This is just the illustration here, and then put iron and nickel here, and the non-metal are usually oxygen and hydrogen, representing the water molecule in our solution. And the nickel divided by iron and nickel will be automatically available in the drop-down menu here, and we will select this as below 0.333. We will include all species that are available because we want to see all possibilities, and we will set the temperature here as 298 Kelvin, which representing room temperature. So let's look at the result here. As you can see here, visually we can see that at 298 Kelvin or room temperature, the suitable condition for the separation process is at pH level below 5 and electric voltage above 0 to make the iron precipitate as hematite here, and nickel is diluted in the solution. We can see this as the blue region here. Or alternatively, you can instead make the nickel precipitate and the iron diluted in the system. Which one do you want to use is dependent on your case. But in here we can see that these two options here are available. So this diagram does not explain how much iron or nickel precipitate, but it's just showing us the tendency of our equilibrium. So if you suppose that you have pH level of 4 and you have electric potential of 0.6, you will probably have hematite precipitate in your system, and the nickel is diluted in the solution, and you can then separate them using normal precipitation method. But it doesn't show you how much iron precipitate or how much nickel is diluted in your system. So it's just showing you the tendency of the equilibrium. In the next slide, I will be using higher temperature at 388 Kelvin, and as you can see here, the tendency is that you will have smaller blue and red gradient here. So what we can see in this case is that by increasing the temperature, we have smaller stable separation region. And then what I did next was that I took 10 degrees Celsius increment or 10 Kelvin increment and simulate all the temperature and collect the result here and animate them. So as we can see here, by increasing the temperature, we actually have smaller separation region. Usually this is not beneficial in our case because we have to add more and more acid in our system with increasing the temperature. So we have to think about actually lowering the temperature so we can have higher pH level to separate our system. So this is just the simple simulation on how we utilize Pourbaix diagram. I hope you can understand it. Comment below if you want to discuss more. Thank you very much for your attention.